The universe. It surrounds us. It is within us. We are a way for the cosmos to know itself. For millennia, humans have gazed at the stars. We have wondered about the fundamental rules that govern all existence. This innate curiosity, this burning desire to comprehend, is a hallmark of our species. We seek patterns. We search for explanations. Physics is our guide on this epic journey. It is the language through which the universe speaks to us, revealing its most profound secrets. From the dance of distant galaxies to the fleeting existence of subatomic particles, physics provides the framework for understanding it all. Our quest begins with giants. Thinkers who dared to look at the world and ask why. Sir Isaac Newton, he gave us laws of motion, simple, elegant, profound. These laws describe how things move, and why they sometimes stay still. Then, there are the great conservation laws. These tell us that some things in the universe are constant, unchanging. Energy, for example. It can transform, but it is never lost. Momentum, too. These principles are like the universe's accounting system. Everything must balance. They are pillars upon which our understanding of the physical world is built. But the story doesn't end there. As our tools became more sophisticated, we peered deeper, into the very heart of matter. And what we found was astonishing. Strange, a new set of rules emerged. Quantum physics, it governs the realm of the incredibly small, the world of atoms and their constituents. It's a world of probabilities, not certainties. A world where particles can be waves, and waves can be particles. This quantum revolution reshaped our understanding of reality itself. It opened doors to technologies we once only dreamed of. These foundational principles, Newton's mechanics, the conservation laws, and the bizarre beauty of quantum physics, are not just abstract ideas for scientists in labs, they are woven into the fabric of our daily lives. They explain why your car moves, why the sun shines, how your smartphone communicates across continents. Understanding these principles is to understand the world around you. It is to appreciate the intricate and awe-inspiring machinery of the cosmos. So let us embark on this journey together. Let's unlock the universe one principle at a time. Are you ready? Sir Isaac Newton, a name synonymous with genius. He laid down 3 laws of motion. These laws became the bedrock of classical physics. The first law is often called the law of inertia. What is inertia? Imagine you are on a bus. The bus is standing still. Suddenly it lurches forward, you feel thrown backward. That's inertia. Your body wants to stay still, or imagine the bus is moving steadily. Then it suddenly brakes, you feel thrown forward. Your body wants to keep moving. Inertia is this resistance to change in motion. Newton's first law states it clearly. An object at rest will stay at rest. An object in motion will stay in motion, with the same speed, and in the same direction, unless acted upon by an unbalanced force. Think about it. A soccer ball sitting on the grass, it won't move, not unless someone kicks it. That kick is the unbalanced force. Once kicked, it would ideally fly forever. But it doesn't. Why? Because of other forces, air resistance, gravity, friction from the ground. These slow it down. In the vacuum of space, far from any significant gravity, if you throw a wrench, it will indeed keep moving, in a straight line, at a constant speed, for a very, very long time. This principle of inertia is everywhere. It's why we wear seatbelts in cars. If the car stops suddenly in a collision, your body wants to keep moving forward. The seatbelt provides the unbalanced force. It stops you, preventing serious injury. Engineers use this law constantly. When designing vehicles, they must account for inertia. Spacecraft use it to travel vast distances. Once they reach their desired speed and direction, they can often turn off their engines, coasting through the cosmic void, conserving precious fuel. Inertia is not just a concept, it's a fundamental property of matter. Consider a simple experiment. Place a coin on a piece of cardboard. Place the cardboard over a glass. Now, flick the cardboard horizontally with your finger. Quickly, what happens? The cardboard flies away, but the coin? It drops straight into the glass. Why? Inertia. The coin was at rest. It wanted to stay at rest. The quick flick of the cardboard didn't apply enough horizontal force to the coin for long enough to move it significantly. So when the support, the cardboard, was removed, gravity took over, pulling the coin down. This simple trick elegantly demonstrates Newton's first law, the majesty of inertia in action. Newton's quest to understand motion didn't stop with inertia. His second law of motion is perhaps the most famous. It connects force, mass, and acceleration. It tells us that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. In simpler terms, if you push something, it speeds up. Push it harder, it speeds up more. If it's heavier, it speeds up less for the same push. The mathematical expression is beautiful in its simplicity. F equals sine ma. Force equals mass times acceleration. This equation is a cornerstone of physics and engineering. Think about pushing a small car versus pushing a large truck. To get the truck moving at the same acceleration as the car, you need to apply a much greater force. Because the truck has more mass, more stuff, more resistance to changing its state of motion. This law is used every day. Engineers use it to design engines for cars, rockets for space exploration, and even to calculate the forces on a bridge. It tells us how much force is needed to achieve a desired change in motion. From launching satellites into orbit to understanding the impact of a collision, Newton's second law provides the quantitative tool. Then comes Newton's third law. For every action, there is an equal and opposite reaction. This law describes the fundamental nature of forces. Forces always come in pairs. If you push on a wall, the wall pushes back on you with the same amount of force, but in the opposite direction. You might not see the wall move. That's because it's massive and well anchored, but you feel its push. This law explains how rockets work. A rocket expels hot gas downwards, the action. The gas pushes back on the rocket upwards, the reaction. This upward push or thrust propels the rocket into space. It's a cosmic dance of opposing forces. Consider walking. When you walk, you push backward on the ground with your feet. That's the action. The ground in turn pushes forward on you. That's the reaction. This forward push from the ground is what moves you, what allows you to explore your world. Even birds flying, fish swimming, they all rely on Newton's third law. A bird pushes air downwards and backwards with its wings. The air pushes the bird upwards and forwards. It's a universal principle. From the smallest interactions to the grand movements of celestial bodies, these action-reaction pairs are constantly at play, shaping our universe, enabling motion. Beyond Newton's laws of motion, there are other profound principles that govern the universe's bookkeeping. Among the most important is the law of conservation of energy. Energy. It's a familiar word. We talk about having energy, about saving energy, but what is it fundamentally? Energy is the capacity to do work. It comes in many forms. Kinetic energy, the energy of motion. Potential energy, stored energy, like a rock perched precariously on a cliff edge. Chemical energy, stored in the bonds of molecules like in food or fuel. Thermal energy or heat. Light is energy. Sound is energy. The law of conservation of energy states something remarkable. Energy cannot be created, nor can it be destroyed. It can only be transformed from one form to another, or transferred from one system to another. The total amount of energy in an isolated system remains constant, always. Think of a pendulum swinging. At the top of its swing, it momentarily stops. All its energy is potential energy, due to its height. As it swings down, this potential energy converts into kinetic energy, energy of motion. At the bottom of the swing, its speed is maximum. Its kinetic energy is maximum. Then as it swings up the other side, kinetic energy converts back into potential energy, and so on. This principle is absolutely fundamental. It governs everything. From the metabolic processes in our bodies that convert food into energy, to the way power plants generate electricity. A hydroelectric dam, for instance. Water stored behind the dam has potential energy. When released, it flows downwards. Potential energy converts to kinetic energy. This moving water turns turbines. Kinetic energy converts to mechanical energy. The turbines drive generators. Mechanical energy converts to electrical energy. At each step, energy changes form, but the total amount accounting for any heat losses remains the same. It's an unbroken chain of transformation. Consider a simple experiment. Rub your hands together vigorously. What do you feel? Heat. You are converting mechanical energy, the motion of your hands, into thermal energy, heat. You did work. Your muscles used chemical energy from your food to create this motion. That chemical energy originally came from the sun, captured by plants through photosynthesis. The sun's energy comes from nuclear reactions, converting mass into energy. It's all connected. The conservation of energy is a powerful tool. It helps scientists and engineers design efficient machines, and it helps us understand the flow of energy that sustains life and powers the universe. An unseen hand guiding all change. Section 5, Keeping it moving. Conservation of momentum and mass. Alongside energy, other quantities in the universe are also conserved. Momentum is one such crucial quantity. What is momentum? It's often described as mass in motion. More precisely, it's the product of an object's mass and its velocity. A heavy truck moving slowly can have the same momentum as a small car moving quickly. Momentum has both magnitude, how much, and direction. Like energy, momentum is conserved in a closed system. This means that if no external forces act on a system, the total momentum of that system remains constant. It doesn't change. The conservation of momentum is dramatically illustrated in collisions. Imagine two billiard balls on a table. One ball, the cue ball, strikes another stationary ball. The cue ball slows down or changes direction. The other ball starts moving. Momentum has been transferred. But the total momentum of the two-ball system just before the collision is the same as the total momentum just after the collision. This is why, in an explosion, fragments fly off in all directions, but if you could add up the momentum of all those fragments, remembering direction matters, the total would be zero, just as it was before the explosion when the object was at rest. This principle is vital in countless applications. Rocket propulsion, as we saw with Newton's third law, is also a beautiful example of momentum conservation. The rocket expels mass, fuel, at high velocity in one direction. To conserve momentum, the rocket itself gains momentum in the opposite direction. This is how rockets accelerate in the vacuum of space. Safety features in cars, like airbags and crumple zones, are designed based on understanding momentum. They work by extending the time over which the change in momentum occurs during a collision. This reduces the force experienced by the passengers, protecting them from harm. Another fundamental conservation law is the conservation of mass. In classical physics, this law states that mass cannot be created or destroyed in ordinary chemical and physical changes. If you burn a log in a fireplace, it seems to disappear, turning into ash and smoke. But if you could carefully collect all the ash, all the smoke, and all the gases released, you would find their total mass is the same as the original log, plus the oxygen it consumed from the air. This principle is a cornerstone of chemistry. It underpins our understanding of chemical reactions. However, we now know, thanks to Einstein, that mass and energy are interconvertible, EMC2. In nuclear reactions, a tiny amount of mass can be converted into a tremendous amount of energy. But even then, a more general conservation of mass energy holds true. The universe is very good at keeping its books balanced. Section 6. Maxwell's symphony, weaving electricity and magnetism. For centuries, electricity and magnetism were seen as separate, mysterious forces. Static electricity could make your hair stand on end. Magnets could attract iron. But the deep connection between them remained hidden, until James Clerk Maxwell, a Scottish physicist, came along. In the mid-19th century, Maxwell wove these two forces together. He created a unified theory of electromagnetism. He did this with a set of 4 elegant equations. These are now known as Maxwell's equations. They are as fundamental to our understanding of electromagnetism as Newton's laws are to motion. What did Maxwell's equations reveal? They showed that electricity and magnetism are not isolated phenomena. They are two sides of the same coin. A changing magnetic field can create an electric field. This is called electromagnetic induction. It's the principle behind electric generators. Conversely, a changing electric field can create a magnetic field. This insight was revolutionary. It meant that these fields could sustain each other, rippling through space as a wave, an electromagnetic wave. Maxwell calculated the speed of these waves, and he found something astonishing. The speed he calculated was exactly the measured speed of light. This was no coincidence. Maxwell had discovered that light itself is an electromagnetic wave, a vibration of electric and magnetic fields, traveling through the vacuum of space at an incredible speed, roughly 300,000 kilometers per second. This was a monumental unification. Light, which had been studied for centuries, was now understood as part of a broader spectrum of electromagnetic radiation. This spectrum includes radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. All are the same fundamental phenomenon, differing only in their wavelength and frequency. So, what are these electric and magnetic fields? Imagine a field as an invisible influence in space. An electric field surrounds any electric charge. It exerts a force on other charges placed within it, like charges repel, opposite charges attract. A magnetic field is created by moving electric charges or currents or by magnetic materials. It exerts a force on other moving charges or magnetic materials. Think of iron filings aligning around a bar magnet. They are tracing the invisible lines of the magnetic field. Maxwell's equations describe how these fields are generated, how they interact with each other, and how they propagate as waves, a symphony of intertwined forces. Section 7. Maxwell's legacy powering our modern world. Maxwell's unification of electricity and magnetism wasn't just a beautiful theoretical achievement, it laid the foundation for much of our modern technological world. The implications of his equations are vast. They have transformed society. Consider the generation of electricity. Most of the electricity we use is produced by generators. These devices rely on Faraday's law of induction, one of the pillars of Maxwell's theory. Moving a magnet near a coil of wire, or a coil of wire near a magnet, creates an electric current. This is how power plants work. Whether they use steam from burning coal, nuclear reactions, or falling water to turn turbines, those turbines spin magnets within coils of wire, generating the electricity that powers our homes and industries. Then there's the entire world of wireless communication. Maxwell predicted electromagnetic waves. Heinrich Hertz experimentally confirmed their existence a few decades later. He generated and detected radio waves. This opened the door to radio transmission, to television, to radar, and today, to Wi-Fi, Bluetooth, and our global mobile phone networks. All these technologies operate by sending and receiving electromagnetic waves. Your smartphone is a sophisticated radio transceiver. It's constantly communicating with cell towers using these invisible waves. All thanks to Maxwell's insights. Every time you use your remote control or listen to the radio or heat food in a microwave oven, you are using technology based on his equations. Electric circuits, the pathways for electrical current, are also understood through the principles of electromagnetism. From the simplest circuit with a battery and a light bulb, to the complex microprocessors in our computers, these all involve the flow of electric charges and the associated electric and magnetic fields. Engineers designing these circuits rely on the laws derived from Maxwell's work to ensure they function correctly, safely, efficiently. Even medical technologies like magnetic resonance imaging or MRI depend on a deep understanding of magnetic fields and their interaction with the human body. MRI provides detailed images of our internal organs without surgery, a powerful diagnostic tool born from fundamental physics. The legacy of James Clerk Maxwell is truly astounding. His four equations don't just describe abstract fields, they describe the very fabric of how energy and information can be transmitted. They are the basis for technologies that define modern civilization. They connect the flicker of a candle, which emits light and electromagnetic wave, to the global internet. They show how fundamental scientific discovery can lead to world-changing innovations. Maxwell's symphony continues to play, powering our world, connecting us, and allowing us to explore the universe in ways he could only have dreamed of. His work stands as a testament to the power of human curiosity and the unifying beauty of physical laws. Section 8. The Quantum Leap, a Strange New Reality. As the 19th century gave way to the 20th, classical physics seemed to have most things figured out. Newton's laws explained motion. Maxwell's equations described light and electromagnetism. The conservation laws provided a solid framework, but a few nagging problems remained, small discrepancies, puzzles that classical physics couldn't solve. These puzzles centered on the behavior of light and matter at the atomic and subatomic level. It was here, in this realm of the very small, that a new revolution was brewing. The quantum revolution. It would fundamentally change our understanding of reality. One of the first strange ideas was wave-particle duality. Classically, things were either particles like tiny billiard balls, or waves, like ripples on water. But light, which Maxwell showed was an electromagnetic wave, began to behave like a particle in some experiments. Max Planck, studying black-body radiation, proposed that energy could only be emitted or absorbed in discrete packets, or quanta. Albert Einstein extended this idea. He proposed that light itself consists of these energy packets, later called photons. So light, it seemed, could act as both a wave and a particle. This was bizarre, but experiments confirmed it. And it wasn't just light. Louis de Broglie proposed that particles, like electrons, could also exhibit wave-like behavior. This, too, was confirmed experimentally. Electrons, which we thought of as tiny particles, could create interference patterns, just like waves. This wave-particle duality is a cornerstone of quantum mechanics. It tells us that, at the fundamental level, the distinction between particles and waves blurs. Things can be both or neither depending on how you measure them. It's a concept that defies our everyday intuition. Our intuition is built on the macroscopic world. The quantum world plays by different rules. Another mind-bending concept is superposition. In classical physics, an object is in a definite state. A cat is either alive or dead, a switch is either on or off. But in quantum mechanics, a system can exist in multiple states simultaneously, until a measurement is made. Imagine a quantum particle, like an electron. It could be spinning up and down at the same time. It's in a superposition of both states. Only when we measure its spin does it choose one state. This is famously, and perhaps misleadingly, illustrated by Schrödinger's cat paradox. A hypothetical cat in a box, whose fate, alive or dead, is linked to a quantum event. Until the box is opened, the cat is, in a sense, both alive and dead. This idea challenges our very notion of what it means for something to be. Section 9. Quantum Mysteries and Our Future. Uncertainty and Beyond. The strangeness of the quantum world doesn't end with wave-particle duality and superposition. Werner Heisenberg introduced another foundational concept, the uncertainty principle. This principle states that there are fundamental limits to how precisely we can know certain pairs of properties of a particle at the same time. For example, the more precisely you know a particle's position, the less precisely you can know its momentum and vice versa. It's not about limitations of our measuring instruments, it's an inherent property of nature itself. The very act of measuring one quantity inevitably disturbs the other. The universe has a built-in fuzziness at its most fundamental level. This uncertainty has profound implications. It means that the deterministic clockwork universe envisioned by Newton is not the whole story. At the quantum level, we can only talk about probabilities. We can calculate the probability that an electron will be in a certain place, or that a radioactive atom will decay at a certain time. But we cannot predict these events with absolute certainty. This probabilistic nature of quantum mechanics was unsettling to many physicists, including Einstein. He famously said, "God does not play dice." Yet experiment after experiment has confirmed the predictions of quantum theory. It is the most successful scientific theory ever developed in terms of its predictive power and experimental verification. Despite its successes, quantum physics still holds many mysteries. The measurement problem. What exactly constitutes a measurement that collapses superposition into a definite state is still debated. The relationship between quantum mechanics and gravity, Einstein's theory of general relativity, remains an unsolved puzzle. Physicists are striving for a theory of everything that can unite these two pillars of modern physics. Ideas like string theory and loop quantum gravity are exploring this frontier. There is still so much we don't understand about the fundamental nature of reality. The quest continues. Yet even with its mysteries, quantum physics has already transformed our world. It's the basis for lasers, transistors, the building blocks of all modern electronics, and semiconductors. It's essential for understanding chemistry and materials science. Emerging technologies like quantum computing and quantum cryptography promise another wave of revolution. Quantum computers could solve problems currently intractable for even the most powerful supercomputers. Quantum cryptography could provide unbreakably secure communication. From Newton's apples to the quantum dance of particles, our journey to understand the universe is ongoing. Each discovery opens new vistas and reminds us that the cosmos is even more wondrous and subtle than we can imagine. The adventure of discovery is far from over.